thanks, Jen, for the intro. And yeah, thanks to you and the EPRV RCN for giving me the opportunity to talk to you all today. Yeah, it's really great to catch you all up on what we've been doing over here in Cambridge and with the Terra Hunting Experiment Consortium. Oh, slide. So in case you don't know me, I'm Sam Thompson from the University of Cambridge. I'm the project manager and instrument scientist for HARPS-3, the instrument I'll be giving you a status about today, and the experiment we're planning on doing with it, which is called Terra Hunting. So before I get stuck into the talk, I just want to give a shout out to the whole Terra Hunting Experiment Consortium. There's 11 institutes involved, so we've all been contributing to HARPS-3, building HARPS-3 so we can actually get on and do the experiment. The PI Institute is the University of Cambridge, headed by Didier Collot, but there are lots of people involved behind these logos here, and the amazing Cambridge team as well that are helping build HARPS-3 and yeah, getting it ready to ship out to the telescope this year. Yeah, our website is here if you want to find out a bit more about us. But yeah, thanks everyone. We're a great consortium, so I just wanted to acknowledge everyone. So starting the talk, I thought I'd better give you a little bit of background and a small apology that perhaps these weren't the slides you were looking for. Sorry for the bad joke. It also is the talk I thought I'd be giving on this date. I think it was towards the end of last year when we booked this slot with Jen, and I imagined that towards the end of March, we'd be packing up HARPS-3, getting ready to ship it out to the telescope. But for any of you who have been following the HARPS-3 project, you know it's been going on for quite a long time, and we have actually been beset by quite a lot of delays and some issues. And even at that date, we did have another delay with the shipping of the final component. And so we don't have actual results that I wanted to show you today of the sort of in-lab verification. But I am really excited to say that we do now officially have all the components for HARPS-3, and it was literally yesterday it was delivered. So the last large optic, which was the camera objective, was actually delivered. So super excited that we finally do have all the parts to build HARPS-3. And so now I can set a schedule to ship HARPS-3 out to the telescope. So I can say for sure that this is really happening this year. So despite what you may have heard in previous conferences of the various first flight dates I've given in the past, HARPS-3 is really going out to the Isaac Newton telescope this year. I've got a bit of a joke here that when we're fully commissioned and we're all happy showing you all the results, you might be able to twist my arm to give the talk at 101 things that could go wrong when you build an EPRV spectrograph. So if you want that talk in the future, just give me a shout, because we've got a lot of things on our list. So just to give you an overview of what I'll be presenting to you today, it's going to be heavily HARPS-3 dominated, with about 20% giving you an overview of the Terra Hunting Experiment at the end. So telling you what HARPS-3 is, there'll be lots of pretty pictures of our components in the lab and our optics, and giving you the actual schedule now of when we can see some real results in the first light of HARPS-3. I'll also be giving you a brief update on the robotisation of the Isaac Newton telescope, because that was another project we were doing, which is a major task in itself as well. And that's exciting news. That's basically done as well. And like I mentioned, what is the Terra Hunting Experiment? The thing we're going to be doing with HARPS-3. So I think I've shown this slide many times before, but this is HARPS-3. So this is a CAD model of HARPS-3. It stands for High Accuracy Radial Velocity Planet Searcher 3. As the name suggests, it has a heritage. It's a closed copy of HARPS from 2003, so over 20 years ago now, and the HARPS North spectrograph over 10 years ago. But it also has some design inheritance from Espresso. It has an average resolution of 115,000, and it's in the visible wavelength range, and it goes down to the near UV at 380 nanometers, and this is so it can capture the calcium H and K lines, which are very useful for stellar activity tracking. You can see the CAD here, so all the main optics are in this large vacuum vessel, and we've got an optical path overlay here as well, so you can see the optical light path. You can see that there's a custom optical table in here that's on 2 layers. There's a top and a bottom layer with the detector units this side, and you can on this sort of seam here, this whole thing opens out, and I'll show you some photos of that in a few slides. And it slides along this 6-meter rail system. So it's a really big rail system, so you can get inside and do your optical alignment essentially. And our RV stability goal for HARPS-3 is 10 centimeters per second over 10 years, and that's to enable the Terra Hunting Experiment. We have 2 fibers that allows a simultaneous calibration mode, and currently our predicted efficiency, not including the slit efficiency, is averaging about 10.7%. But of course, we'll be measuring that in the lab and confirming that over the next few months. And the big change with HARPS-3 is that it's all going to be embedded in robotic operations. So we've also got lots of extra sensors and essentially, electronic control, so we can really efficiently execute our program. To go into a few more details of HARPS-3, and I've got some slides going into a bit more details on some of these points in the next few slides. We've also got a deployable full-scope dual beam polarimeter that's installed at the CAS adapter on the telescope end. So you can sort of insert that in and out and essentially have a spectropolarimetric mode for HARPS-3 as well. In our calibration unit, there are 8 switchable light sources. So that's what this diagram is showing here. We have your sort of usual suspects. We've got thorium, argon, spare. These are just the white light sources. We've got a uranium neon, Fabry-Perot-Etylon. We'll also be quite excitingly getting, well, hopefully getting a full spectrum laser frequency comb. So this, there was a paper published last year by Harriet Watt and us in collaboration, testing out a new type of waveguide that provides this broadband, goes down to the near UV. And I'll show a slide on that in a few slides as well. And our spare slot hopefully will be populated with a Boris, which is a polarizing sun as a star telescope. And so you can check out the poster by Casper and Anneliese here if you want to find out a bit more information about that. And you can essentially put any combination of these down, our fibers A or B. And yeah, so some of the design inheritance I mentioned from Espresso is that in the calibration unit, we have improved scrambling there and wedge filters to avoid fringing effects. And I already mentioned full wavelength range laser frequency comb. As well, design inheritance, we have a miniaturized Espresso cryostat design. So hopefully that will give us improved temperature stability of our CCD. When we were purchasing, so the big shell grating, it's the main, the high resolution dispersion element. It's really long, 840 mils in length. And so we upgraded the zero jaw for that. So that's a more stable version, more thermally stable version of zero jaw. So any extra stability you can get, the better. As well, trying to minimize any sort of potential sources of RV error in the instrument. And even though we've got really good scrambling everywhere, you want to sort of minimize your possible source of illumination variation. So we have an on-fiber guiding accuracy goal of 0.05 arc seconds RMS. So that's the fast tip tilt mirrors pointing the star onto the entrance fiber. We're going to have a new 2-color exposure meter that's been designed by my student, Alicia Anderson. And we'll be using the Espresso data reduction pipeline that's configured for HARPS-3. So I wanted to give you a brief update on the HARPS-3 polarimeter. I don't know whether you've been following the papers, but there's 2 papers. Patrick Dorville's paper goes into full details about the design of the polarimeter in the 2018 paper. But in the paper last year, it was reported that there was a serious issue with the polarizing beam splitter. So here's our standard observing mode. This is essentially the star coming through the telescope. We've got our atmospheric dispersion correctors here, the fast tip tilt mirror I just mentioned, pointing to the fibers aren't shown here. And this is these are the polarizing optics, and they are on a linear slide. So they are literally deployed into the beam here. So you have the half-wave plate, and this is the polarizing beam splitter that had the problem. I should mention that you can't use simultaneous calibration mode when the polarizer is deployed, because of course the light is split and both channels are used for the different polarization states. And so, yeah, there was quite a serious degradation of this polarizing beam splitter over the years that was being monitored. There'd been some issues in the manufacturing of it, and it was determined. So Patrick, it was basically non-functional. So we needed to make a new polarizing beam splitter So I wanted to report, in case people were worried about that the new polarizing beam splitter has been manufactured and will be installed before HARPS-3 is shipped. So hopefully we'll have a fully functional polarizing beam splitter, and the expected performance is supposed to be similar to that of HARPS-POL on the ESO 3.6 meter telescope. And a slide about our laser frequency comb that we're planning. So this is being designed and built by Heriot-Watt University in collaboration with us. This is a figure from the paper last year, here referenced in Nature Communications. As you probably know, the laser frequency comb is your ideal calibration source. It's got extremely narrow intrinsic line width, so unresolved by the instrument. And we want to be able to use those to measure and track the instrument profile. And hopefully it's stable, gives us a really good, stable and accurate wavelength calibration source as well. Our goal for the HARPS-3 laser frequency comb is to have comb lines in every order of HARPS-3. So far, it's already been demonstrated down to 385 nanometers. And it's using this new, you can see this really cool glowing waveguide up here in the figure. It looks quite exciting. I'm not going to, it's periodically poled lithium niobate ridge waveguide. It's a bit of a mouthful. And it's using a combination of second harmonic generation and some frequency mixing. Don't ask me to explain all the details, but it can generate this sort of down to the near UV broad spectrum comb, which is really exciting. So in this paper, it was showing from 385 to 510 nanometers, and there'll be a red arm to cover the rest of the wavelength. The comb line spacing is going to be something between 18 and 30 gigahertz. It will be tuned specifically for each arm of the laser frequency comb. So it's going from like red to blue here. And it's going to be delivered later than the main HARPS-3 instrument, so probably towards the end of next year. And I mentioned that we'll be using the Espresso data reduction pipeline adapted for HARPS-3. And so part of our task, because of course we count the data reduction pipeline as part of the instrument, because without that you can't analyze your data. But so part of our task to understand all the instrument-based sources of RV error better than 10 centimeters per second. We want to fully understand, sort of do end-to-end testing of the data reduction pipeline to check if there's any sources of bias or algorithmic error that comes in, in different conditions, different signal to noise of the data. So Alicia, so here's a picture of Alicia writing a paper on this, but she's been writing software to generate fully simulated raw data images for HARPS-3. So this is an example of one of the frames. Sort of zoom in here. You've got in fiber A, we've got a Phoenix, it's generated Phoenix spectrum with solar parameters, and on fiber B, we've got a thorium argon spectrum. And the idea is, yes, we can generate all the different sets of raw data that we're going to have for HARPS-3. You know exactly what you're putting in here, so we can introduce things like, a Doppler shift on the spectrum, change the different noise in the images, and do a whole load of different end-to-end tests of the DRS and see what errors and biases might come out, and anything that we should be concerned about at this level, of course, that we're trying to get down to for Terra Hunting. And that will also be really useful to help us disentangle software-based errors and specifically hardware-based errors. And so Alicia's writing that paper at the moment, and hopefully we'll be able to present some more results on that at EPRV 6 later this year. So keep an eye out for that. So you'll want to see that HARPS-3 is real. So I've got some pretty pictures to show you of HARPS-3 in the lab. So this is from one end of the vacuum vessel. So if you remember the CAD diagram I showed you earlier, this is the big vacuum vessel, nearly 3 meters long on the 6-meter rail system. And yeah, this is our big gantry crane moving everything. This is a very large, it is where all the calibration light sources, which I mentioned. So this is where all the thorium argon lamps and essentially all our spectral calibration lamps are in this cabinet. This is a picture of the CAS adapter, the cassegrain adapter. This is, you can see there's a big plate here. This is what bolts onto the end of the telescope. And it's where the polarimeter lives. So the polarimeter lives in here, the deployable optics. on all the other optics, such as the ADC, the tip tilt mirrors. There's quite a lot of optics packed into this little unit here that's essentially taking the telescope focus and refocusing it onto our fibers to take down to Harts 3. And this is just from the other end of the vacuum system. So these are all the ports. So there's a lot of this business end of Harts 3. We haven't, this picture was taken a few months ago, so these aren't populated in this picture. This massive port here is where the detector unit is going to be inserted. And there's a picture here of it opened. As I mentioned, the whole thing opens out on the rails, and it's incredible. The system is so, with this system here we've got on the rails, it allows it to be really flattened, and it's a really smooth rail system. So you can literally just, one person can pull this open by themselves. It's just a really smooth rail system, which is quite incredible given there's several tons here of steel. And this lets us get to this custom optical table where all our optical components are going to be installed. So you can just sort of see the arm here that's going to support the large collimator, and our shell grating will go here. The camera is going to fit under here. Things are starting to be plugged in on this picture. So I wanted to give you a bit of context for my advert slide. You probably, I was in disguise inside of Harts 3. So this is when we had the vacuum vessel opened and we were installing, this is an aperture mask that goes in front of the grism. And you can see looking down the chamber inside here, and it just seemed like an entertaining opportunity for a photo. So my face is in place of the grism. So to remind you of the optical layout of Harts 3 before I show you the individual optics pictures, the light is injected here. So this is the fibre exit. So it comes out at 1. We've got our large 770mm diameter collimating mirror, which collimates the light and puts it on the large shell grating, which is our main dispersing element. It's reflected back onto the collimator. There's a very thin, I don't know if you can see it, but there's a very thin flat mirror here, which puts it back onto the collimator, and then it's going through this optic here. 5 is our cross disperser, because of course this is giving you very high resolution spectrum at high orders, where they're all overlapping, and so the cross disperser is separating it in the opposite direction. And then from here to here is what we're classing as our camera objective. The actual barrel is only from the lens are mounted inside a barrel from L1 to L5. So the optomechanics are sort of housed here. L6 is free floating part of the camera objective because it's actually used as the detector cryostat window. And I'll show you some pictures of these. The exposure meter optical path is not shown on here, but I'll mention a little bit about that on the next slide. So to show some of our smallest and largest optics, I can't resist showing this one because no one can say optics aren't cute. This is one of the smallest. It's only 5 mils here. This tiny prism assembly with micro lenses on it. So it's part of the exposure meter optical path. That was just me being silly because I think they look kind of cute. And this is our largest optic in this dimension. So this is 840 mils in diameter, the shell. You can see we've illuminated it from underneath here. So this is a mosaic grating because you can't make one this long. So the 2 grating faces are replicated on separately and perfectly lined within like half a wavelength. But there's this, you can see this gap glowing here. And so this light isn't wasted. We put a very long, thin mirror in this gap, which diverts light from what otherwise would just be sort of lost or scattered in the system into the exposure meter path. So this is sort of essentially the collecting area where we sample light for the exposure meter. And this is our big 770mm diameter collimator when we were inspecting it. And this is a picture of the grism. It's the cross dispersing element I mentioned, and things look really cool through the grism. So this is just looking onto the Harts 3 vacuum vessel through the cross disperser. The world looks very cool through that. It's it's a nice rainbow view of the world. And this was us testing the grism to check that it had been printed the right way up. So GRISM, if you're not familiar with the word, is essentially a combination of grating plus a prism. Essentially, you've got this big block of glass shaped, it's the prism. But on one of the surfaces, you have a resin grating face applied. And yeah, you want to make sure that's printed the right way up. That didn't happen to Harps 3, although I do know of colleagues where it has been printed the wrong way. So with that in mind, we're checking essentially that yeah, the dispersion's happening as we expect it to happen. And yeah, this was all good. Although I should mention this was the second GRISM we received. So we did have a few hiccups with it was that the first one was damaged on delivery, so wasn't completely smooth sailing, but the GRISM was applied the right way around, and it looks very beautiful, as you can see. So this is what we're very excited about the past couple of weeks. Our last main optical component was the camera objective, which was finally delivered yesterday. This is myself and Clark Baker visiting Thales SESO last week for the preliminary acceptance review. This is part of the Thales SESO team, and yeah, this is the Harps 3 camera objective. We were inspecting it and getting the full rundown of the various athermal locking mechanisms and things like that. So yeah, we had a successful preliminary acceptance review, and delivery was literally yesterday to prove it did actually turn up. Thanks to Ali, our engineer, it arrived very earlier than we were expecting, but he was on site and took this photo to capture it. It's an immense occasion of getting into our lab. So yeah, we haven't actually had a chance to open the box yet, but we'll be doing that tomorrow. So really exciting news that we can get ahead and install all the optics and do the full optical alignment now. So we will actually have a functional spectrograph. And this is part of the L6 assembly. And talking about L6, this is the final lens in the camera objective, but it's also acting as our cryostat window. So you can see it has this quite unusual shape. It's actually a very difficult optic to make because it has this sort of, you can see it's like a flange shape essentially, because that's fitting in, it has to act as a vacuum seal and the cryostat window. But there's two specific surfaces here. You can see it's quite highly curved. There's a cylindrical surface on one side and a spherical surface on the other. You can probably, if you're beady-eyed, you can see that there's a mark here marking the cylindrical axis. It's a really beautiful optic because it's highly polished. This one, because of course it's so close to the detector plane, you don't want any scattered light. So yeah, L6 is actually a very beautiful optic. And so L6 fits in the detector head. This is the detector head dismantled for this picture, as I was mentioning about unexpected tasks and added to the list of the 101 things that might go wrong as you're building an EPRV spectrograph. So we had a problem with the readout of the CCD in that only opposite quadrants of the CCD were reading out, and we weren't getting any readout from the other quadrants. And so we found out that there was a break in essentially in the flex connectors that connect essentially the detector to the outside world. So we had to, this isn't something we're very familiar with, but we are now. We had to do a complete strip down of the detector head, which is quite a complicated operation, and get into the depths of essentially this PCB board. Here you can see I've labelled which were the two faulty flex connectors, and there was a broken line on each one. The annoying thing is you can't just unclip the cable and put a new one in, because these flex connectors are soldered onto the back of these hermetic connectors. So you have to completely take them out, desolder. There's about 40 odd connectors here. Desolder all that, put that all back again, and reassemble this. You might be wondering what this is. This is because this is a sort of sprung-loaded thermal finger that goes onto the back of the chip carrier that conducts essentially from the continuous flow cryostat, which is below here, to above, and that's just to stop the whole spring system collapsing downwards. So yeah, we've done a full strip down, replaced these cables, and put it all back together again as one of our unexpected tasks, which did add a couple of months to our schedule. This is the G5, so this is an engineering grade CCD. It's not the final CCD at this point, because we want to do all the full tests first to make sure everything's everything's good and working. We don't want to risk our scientific grade CCD until we're sure everything is working perfectly. So this is now installed back in the refurbished detector head. This is not L6 at the moment, but this is just a flat window we're using for testing. A new flange with L6 will be installed very shortly. As you saw, it's just arrived, and we'll be putting that in. And the very exciting news, another big milestone, was last week we had the first successful CCD readout after the repair work. So we're really excited about that. It's been a really big job to get that all fixed. So yeah, this is everything all hooked up. You can see our sort of liquid nitrogen cryostat, all the cables connected. So we have a functioning detector unit now, and we're really happy, and we've got all the optics to go with it. So I can actually confirm a schedule now for the first time. So from now until middle of June, we'll be doing all the subsystems integration and testing for HARPS-3 in our Cambridge lab here. Then essentially we need to dismantle everything, pack it all really safely. There's like nearly 7 tons of equipment that we have to pack, and they will be going into 2 20-foot shipping containers. So that's you can imagine that's quite a lot of equipment that's going out. We expect that transport to go from around mid-July. So this is going sea freight, essentially from a UK port to La Palma. The journey of that depends on the exact route you book, which we haven't booked yet. You have to book yourself on one. The expected arrival on La Palma is somewhere around the last week of August. So then we imagine we're going to start installing all the HARPS-3 systems around the end of August. And then a month after that, we're expecting HARPS-3 first light. So that's when we plug the fibre from the telescope end into HARPS-3, and we get our first starlight on the detector. So that's going to be really exciting. And then about a month after that is around the expected end of commissioning, before we hand over to, say, community science verification or the start of the Terra Hunting Experiment. So I think I already mentioned it, but yeah, HARPS-3 is going on the 2.5 metre Isaac Newton telescope in the Canary Islands. This has been a big project that's been running alongside HARPS-3, has been the roboticization of the Isaac Newton telescope. It's like 50 or 60 years old, started life, Herstmonceux, south coast of England, got shipped out to La Palma in the 80s, has been there, but the system's all basically obsolete, coming to the end of life. There weren't really any spare replaceable parts, and so if you're trying to run a really efficient 10-year observing program for Terra hunting, we couldn't risk the whole thing breaking down. So it's been fully refurbished and enabled to robotic operations. That whole refurbishment is complete, and there's final acceptance this month. So this is another really exciting thing that's happening. Everything's happening at the same time, as you can tell. As part of sort of robotic software systems, there's an automated scheduler that's been designed by University of Exeter, and that will take essentially the mix of Terra hunting and open time observations and optimally schedule them. So depending on what you've put into your phase 2 request, like if there's specific bright or sort of seeing conditions, what have you, it's going to essentially decide the optimum conditions for your observation. The one thing I forgot to say as well is that the on-sky fibre diameter of for HARPS-3 is 1.4 arc seconds. That's a bit different to HARPS and HARPS North, which is 1 arc second. That's just to do with the focal ratios involved at the telescope. But this is pretty good actually, because this is well matched to the 80th percentile of seeing conditions at the INT. So it means we get a lot more light going through. So that's a really good bonus there. So the expected photon noise for our faintest target, which is 7.5 GMAG, G8 star, is around 25 centimeters per second. That's a 15-minute exposure in average seeing conditions. And as a reward for essentially building HARPS-3, bringing it to the Isaac Newton telescope and fully refurbishing the telescope, we're going to get nightly access to the Terra Hunting Experiment for 10 years. So that's really exciting. This is what is going to enable us to get a really well time-sampled RV data series, to do Terra hunting. The other half of the time is going to be open time via the ING, and keep an eye on their web pages for more information about that. So to show you a few pictures of the telescope, in case you're not familiar with the Isaac Newton telescope or haven't done observations there before, these were the sort of older push button systems. They look pretty cool, but they're not there anymore if you were in love with them. So this is the old system, sort of essentially a manual operation system. A very scary clip center where all the wires converged. So we've gone essentially from a centralized manual control system to a robotic distributed control system. And you can see here's one of the new control cabinets. Got a nice view of the INT through here. Clark's taken a really cool picture here. And this is a nice sort of engineering GUI where you can control the telescope from. It's fully robotic. The team that did that, the contractors, Project Soft's done a fantastic job. Yeah, it's all modern PLCs, and it's really exciting that the INT has got a new lease of life for decades to come. So really fabulous there. And showing exactly where HARPS-3 is going, I should have said in the previous slide, one of the cool things about the Isaac Newton telescope is that when it was built with dedicated Coude rooms, which were never actually used. And although we're not doing the free space Coude path that was envisioned, the fibre, we'll have a fibre following that path instead. It does mean we have a lot shorter sort of fibre routes, which again gives us a good boost in the blue efficiency. So yeah, we'll be going in the East INT Coude room. This was the room before. It was INT have lost some storage space. So the IAC have refurbished this. This picture was taken in August last year before the refurbishment was complete. And this is just part of one of the rooms. There's several sections of the rooms. You're sort of coming through these doors. And HARPS-3 is actually going to go into a room that's through here. But you can see there's been a lot of different things going on. And yeah, we're really excited to bring HARPS-3 and install it here in the next few months. Oops, too far. So yeah, I'll tell you now a little bit more about Terra Hunting Experiment. So you can imagine now that we've got HARPS-3, we've verified it on Sky, it's all looking good, and we're ready to start the Terra Hunting Experiment. And you know, what is that? Essentially, it's going to be a 10-year program to try and detect a 10 centimeters per second RV signal of an Earth twin around a solar-like star. So nearly 10 years building HARPS-3 and another 10 years doing Terra Hunting Experiment. So we've got a nice weighted scales there. As I mentioned, we've got an average of 50% of every night on the Isaac Newton telescope for 10 years. And this is going to enable an intensive optimized observing strategy, which we really need to try and dig down and get that signal to noise that we want. Probably looking at over 1,000 observations per target. And all of that is going to be realized using this sort of efficient automated scheduling. A very brief overview of what our targets are going to look like, but they're going to be brighter than a G magnitude of 7.5. They're solar type, so we're saying G to mid-dwarf type stars. Our sample size is probably going to be something from around 22 and maybe up to 50, depending on the exact sampling strategy that we go for. We do need a minimum observability of 6 months and at an air mass less than 1.5. Again, this is for RV accuracy reasons. So that's our sort of minimum observability for a target. And given our sort of 1.4 arc seconds on sky fiber diameter, you can imagine we don't really want any spectral contamination. So a close binary or spectral binary or other possible sources that would make our job even harder of disentangling multiple spectrum. So these are the kind of basic checks that we'll be doing on our targets. And we've got quite a comprehensive list of goals on our website if you wanted to read a little bit more about them. So we've got a sort of priority list of goals. And I think I've shown this plot many times, but it is a cool plot. It's the sort of mass period discovery space of planets that have a measured RV. So we've got minimum mass on the y-axis here, orbital period, and sort of sketched on probably a very low threshold here of our current limitations around 50 centimeters per second. And you can see that there's a lack of observations down in this sort of long period, low mass regime. Our own Earth has been put on here. So the color coding is actually to do with stellar mass. So this is our sun and the Earth at 9 centimeters per second, 365 days. And so this is the region now we're all trying to get down with our EPRV spectrographs. And so, yes, we're trying to open up this parameter space for HARPS-3, trying to find planets in this sort of 60 to 400 day orbital period and sort of around 1 to 4 Earth masses, essentially to show that they exist, and finding them will provide some really cool targets for the future direct imaging missions as well. And can't resist showing the great HARPS North Solar data set, which is sort of illustrating the challenge of stellar activity that we need to overcome. I've overlaid, plotted on the signal of an Earth. So this is a 9 centimeters, 365-day signal of Earth on top of this. And this is what we're trying to find. So obviously this is the regular Doppler shift on a 1-year period. And we've got these quasi-periodic signals of different amplitudes varying on different timescales of the various sources of stellar activity. So there's quite a challenge here to beat down the stellar noise and dig out this signal. But we shouldn't forget the instrument as well, because essentially a Doppler shift of 10 centimeters per second, only 10,000th of a pixel. That's literally 4 silicon atoms on our detector. That's a pretty serious challenge that we're trying to say that we want stability of our instrument at this level over 10 years, and we've got to sort of demonstrate what that was, understand all our systematics, keep track of that, keep our signal to noise at such a level that we have confidence in any signal that we find. So we've got lots of challenges, but some very exciting science ahead of us to get to realise this picture. So to give you a summary of the sort of history and where we're going with our survey strategy for terra hunting. So our baseline strategy, which I think I presented in EPRV 3, I think it's quite a while ago, was this once per night, 6 months per year for 10 years. And that was Richard Hall wrote a nice paper on that in 2018. So since that time, we've been trying to decide, is that the best strategy? Recently, I'd say over the past few years, we've been thinking about maybe it'd be better to have a tiered survey. So essentially, we start with a lot more targets. So we have a very long target list of several hundred targets at the moment. But you might want to pick, say, I don't know, the top 100 of those. And we spend maybe 1 or 2 years doing a sort of detailed target characterization survey, thinking that we can understand some interesting parameters of the stellar activity, for instance, that we might decide that some targets are better for looking for Earth-like planets around than others. And then you can think we're going to go on to our main survey, where we are then settling into essentially our optimized strategy per target to dig down into this 10 centimeters per second level. So in terms of the season window, I mentioned, 6 months we've written here, but we know that a longer season is better. You might be wanting something like 220 days, for instance. This is so you've got better period detection on your planet. But of course, as you extend your season, you're reducing your number of targets. So there's a balance to be had here. So in terms of the actual sampling strategy, so not just the length of what you're sampling over, but also your inter and intra-night sampling. You want to sort of minimize aliasing between all the different signals in your data set. So again, with your observation window, and potentially you might have multiple planet systems in there. You've got all the different stellar activity signals in there. Any signal you can think of that could be in your data set you want to be concerned about. So do we do sufficient sampling to allow the modeling of all those components, or are we going to do something, say, to average out those? So you might think, so in terms of P modes, you could do an exposure time that essentially averages out to a level you're not worried about anymore. You also want to think about the rotation period of the star, because of course these magnetic activity signals are being rotationally modulated by the star. So you want to probably get sufficient sampling over the rotation period. And yeah, all these sources of stellar activity I mentioned, such as granulation, supergranulation, things to be concerned about. And yeah, we've just got to decide what's the best sampling strategy to enable us to model or minimize those signals. And as I mentioned, depending on what strategy you go for, the season window, the exact number of data points you're taking per star, is all going to affect how many targets you end up with. So this is a sort of interesting optimization problem. Just wanted to add a couple of extra notes on the survey strategy. So there was Arvind and Megan's very nice paper last year with fishing for planets. So this was looking at the fisher information present in the data set with various sampling strategies. And they demonstrated a general preference for a single visit per night, EPRV surveys like the Terra Hunting, but that they also showed that the optimum sampling across the seasonal baseline is probably best tuned depending on the correlation timescale activity on a given star. So this is why we've been thinking about why a tiered survey might be better, because we could learn a bit more about the activity type of the star, what the correlation timescales are looking like. It just helps you better decide on the optimum sampling strategy for that particular target. So just compare that with our baseline strategy. We're aiming for older solar-like stars, so we will be having sort of longer rotation periods. And yeah, Arvin and Megan's paper seems to agree that the approximate once per night cadence spanning a long season baseline is likely the optimum, but I think it's just something we want to test. So I mentioned about one of the sources of stellar activity, P modes, which we think we're okay with because we'll essentially take a long enough exposure to minimize the residual amplitudes there. This plot here is the expected photon noise limited RV error for HARPS-3 against the magnitude of the star. So here's the limits. This is our sort of faintest star we expect to have, and this is our 10 centimeter limit. And there's some very spectral type stars here for different exposure times. So just to highlight, for the 15-minute exposure of the sun, we have a signal to noise, expected signal to noise around 210, and photon noise limited error of 25 centimeters per second. And our main aim is that I think we want very good signal to noise spectra, because Michael Chrétien's paper here showed there's very nice that PCA shell analysis, but you need very high signal to noise spectra. So we will be setting a minimum signal to noise ratio for our targets, and the idea is we'd expose to get that signal to noise, so it might not be 250, but that's just an example, and then we'll tune the exposure time to minimize the P mode amplitude to be below 10 centimeters per second, say. Yeah, this is the figure from Chaplin showing this this residual amplitude versus integration length time. So looking ahead, if you've been following this, you realise that I haven't said anything completely new there. So there isn't any particular new update to the Terra Hunting strategy at this time. The plan for the initial tiered survey is going to be decided over the next 7 months, so before operations start. I will mention that our target list will be published on our website, so that will be freely available for everyone to look at what we're observing, what we've decided to drop, etc. And personally, I just want to say I'm really looking forward to collaborating with the other EPRV instrument teams as part of the EPRV RCN Standard Stars programme. We've already been doing some really cool work together, and I'm really looking forward to bringing HARPS-3 into the mix so that we can all be comparing our data and yeah, trying to push to all our common goals of getting towards 10 centimeters per second. So I'll summarise with this slide to say lots of exciting news that the INT robotic upgrade is complete with final acceptance this month. We have got a set schedule now for HARPS-3. So we're definitely shipping out to the Isaac Newton telescope in July. And so we're starting commissioning around the end of August. Open time is going to be available for HARPS-3. So if you're interested in that, please keep an eye on the ING web pages. Possibly the first proposal call will be coming out in late 2025. There may be some other opportunities that are going to get advertised, such as, say, community science verification, and it'd be great if people would want to get involved in that. So please keep an eye on those web pages for that call. And yeah, a very brief summary of Terra Hunting, that we're hoping to probe that new parameter space of 1 to 4 Earth mass planets in that long period 60 to 400 day orbit regime. We've got a lot of time on the Isaac Newton telescope, so we can get this really great sort of intensive optimum sampling strategy for Terra Hunting. We haven't quite decided on our strategy yet. Probably it's going to be a 2-tiered survey, and that we're going to be optimizing the strategy depending on what we learn about each target. So yeah, thanks for listening, and I'll take any questions.
Excellent. Thank you so much for a really great presentation, Sam. While folks in the audience ponder questions for a moment, I'll start with the two that were asked in the chat during your talk. So Chad was asking what the bench is made out of.
It is steel with a nickel coating.
Okay, thanks.
Okay. And then Andre asked, is there a plan for interventions in the instrument? If not, do you have an idea of how the possible RV offsets would impact your primary science goals?
Hang on, let me read that. Interventions.
I think if you need to open it up and make changes to things, especially early on.
Ah, okay, yes. So until we get the laser frequency comb, that is a potential issue. So one of the benefits of us, say, not starting the high precision part of our survey, doing the tiered survey, will be timed as well for when we get the laser frequency comb. So if we're starting, say, a 1-year tiered survey from the end of this year, then by the time we start, say, the one where we start worrying about 10 centimeters per second, would be there when we got the laser frequency comb. So we hope to be able to essentially be completely tracking the instrument profile by that time. If that answers your question.
Yes, he says in the chat.
Cool.
Other questions from the audience, please feel free to raise your hand or just unmute and ask. I think we're a small enough group for that today. So do you have any, I don't know, either hopes or concerns about the installation process at INT? Is there anything that you think will be especially challenging given the refurb looks like it's going wonderfully, but you're still installing into a relatively old facility? Anything that you're concerned about?
Not at this moment. I mean, I'm not. You can't rule anything out. I feel like almost any sort of. We've had a lot of things happen. So yeah, I think in this game you can't rule out unexpected things, and it's the things you possibly haven't thought about that are going to bite you. But hopefully we're on a clear path.
We're just saying while you were speaking that we should, at one of the future EPRV conferences, each team gets like 1 or 2 slides to highlight the worst thing that happened during their build process, and we can have a competition for who had the hardest time getting their instrument actually on Sky.
That would be amazing. You might get bored.
We'll let you guys finish first. We'll pitch it for EPRV 7.
Arvin's got his hand up.
Yes, Ivory, go right ahead.
Yeah, thanks, Sam. Cool talk. Thanks for the update on the instrument. You may have said this, but I'm curious what the readout time is for the exposures, just in terms of thinking about P mode, integrating over the oscillation time or sampling it.
So we are going to enable, I suppose we haven't completely decided, but it depends exactly on how many channels there's up to 4 channels you can read out of. Probably we'll read out of 2 parallel channels, maybe 1. But if we say go for 2 channels, it's Hops North mode. I think that's 23 seconds if I remember. I'm trying to remember exactly. I've been looking at too many numbers recently of the different channel readout modes, but I can follow up and send you that number. I think it's less than 30 seconds.
Okay, yeah, thanks. I might send you an email to follow up about that.
Yeah, cool.
Eric Ford in the chat says, exciting. I totally get the idea of a tiered survey, but I might have expected that you'd start with 1.5 or 2 times more stars than you intend to continue intensively. Did you say that you were planning on much more than this? If so, could you explain why?
So we haven't completely decided how many we'd do in the finals, because I mentioned 22 to 50 for the final survey. And so I was thinking that we might have up to 100 in this tiered survey. So this is part of the planning over the next 7 months where we're really going to dig down into those details. So it is about what you said. And also depending exactly on what we want to study for those targets as well. But yeah, things like, say, if you wanted to understand, say, the supergranulation signal, that does require a bit of a intensive period on each star. So those are all just calculations that need to be made and then decided how much time we want to have in this tiered part, and then how many targets we can actually look at.
Eric, does that make sense? Thanks. Other questions for Sam about HARPS 3 or about Terra hunting? Can you talk a little bit, because I haven't seen this before, a little bit more about the exposure meter and this idea of pulling the light from between the mosaicked grading pieces?
Yeah, essentially, there's just a long thin mirror that essentially just sits in front of there, so it doesn't really interfere with the main beam because it's in the gap essentially, and it's just directing it off at an angle to another big optic, which then focuses it down and essentially takes it. It gets focused onto some fibers which go out of the chamber essentially and into some photomultiplier tubes.
Nice.
So it's just taking that what would be strip of wasted light out of the system where we measure it in some photomultiplier tubes, because of course there's actually quite a small amount of light there.
Yeah, I was going to ask if the physical restriction of how much space you had there was going to cause either challenges or limitations.
That's why when Alicia's to redesign, because we thought it would be nice to have a colour split so we could have a red-blue split, because the HARPS and HARPS North have got a white light exposure meter, but purely because of the fact we don't have that much light, we can't split it more than 2.
Okay, any other questions from the audience? Okay, well, if not, let's say thank you again to Sam for a very excellent presentation and a super exciting update on where things stand. I think everyone's very stoked to see this instrument get on Sky later this year. Thank you all for calling in. We'll be back next month, 4th Thursday of April. We're still finalizing speakers, but by that point, I think we will have everyone will be back on the same daylight savings alignment, and so we'll go back to the normal time spread that everybody is used to. So take care in the meantime, folks, and catch you all in April.
Thanks, everyone.
Thank you very much.